This is a short tutorial on electron configuration theory and how sublevels split based on energy. In the hydrogen atom, which is the easiest one to consider, the sublevels S, P, D, F all have the same energy. When we have the same energy for these different orbitals, we refer to them as degenerate. As long as they have the same energy, then it doesn't matter which of the orbitals the electron ends up in. In multi-electron systems, though, the energy levels split based on the value of L. In general, the relative energies look like this. S orbitals are lower energy than P orbitals, that are lower energy than D orbitals, and finally lower energy than F orbitals. If we were going to place an electron in an n equals 4 orbital, we would first place it in the s orbital because it has lower energy in the p. We would next put electrons in p orbitals and then d orbitals in f orbitals based on the energy. What we find experimentally is, in principle, this is the order that they fill in, although there were some exceptions. Well, if that's the experimental what, the theory that we're going to talk about in this tutorial is the why behind the experimental results that we always see. To understand the why of energy splitting, we must first consider Coulomb's law. Coulomb's law governs the attraction or repulsion of charged particles. Here we can see Coulomb's law stated as energy equals 1 over 4 times pi times a constant called the permittivity of space times the charge on one particle times the charge on the other particle divided by r, which is the distance between the charges. Specifically, when we're considering electrons and protons, Q1 equals +1 for our protons and Q2 equals -1 for our electrons. Energy is positive for particles with the same size, and plus energy is repulsive. If we want to think about this in terms of thermodynamics, this is an endothermic process. We have to invest energy if we want to bring particles together that have the same sign. Energy is negative for particles with different signs, i.e. +1 times -1 is a negative value. And that would be an energy of attraction. Again, considering thermodynamics, we would talk about this in terms of being an exothermic process. As we bring particles together of different signs, there's a release of energy. We're talking attraction then between the nuclei, where Q equals plus times the number of protons in the nucleus, and electrons, where the other Q is a -1. And additionally, we have repulsion between electrons in different principal quantum numbers n, and repulsion between neighboring nuclei as we're bringing two atoms together to form a bond. We're going to look at how Coulomb's law affects something called shielding, and we're specifically talking about electron shielding. Our nuclei may contain a large number of protons, which in Coulomb's law makes Q1 a large positive number. We should ask ourselves the question, are all of the electrons affected in the same way by these protons in the nucleus? The answer is no, for two different reasons. The first reason is R becomes larger as n increases. So the electrons in n equals 1 are much closer to the nucleus and much more strongly attracted than the electrons in n equals 2. So if we take a look at the diagram shown below, we can see that distance has an effect. We also have to consider shielding by electrons in lower n levels. So for our n equals 2 electrons, in addition to the attraction to the nucleus, we also see repulsion between the electrons in n equals 2 and the electrons in n equals 1. This shielding is electrons at lower n values pushing back. So for n equals 2, the electron binding energy is the energy of attraction between the electrons in n equals 2 and the nucleus. Attraction to the nucleus should give us a negative value for E. We then also have repulsion from the electrons in lower principal quantum numbers, in this case from n equals 1. We're going to then add that energy of repulsion, and because we're dealing with shielding where we have the same sign charge on Q1 and Q2, we end up with a positive value. So when we're evaluating the electron binding energy, we have the energy of attraction, which is negative, plus the energy of repulsion, which is positive. Well, we're going to have to take these repulsion attraction values into account as we're filling orbitals, and specifically as we're filling the sublevels in each orbital. So if we take a look at an energy diagram, typically shown here, energy increasing as we move away from the nucleus, we can see that the lowest energy orbitals are 1s orbitals. They are the closest to the nucleus. As we move away from the nucleus, we then have our 2s orbitals, which are closer to the nucleus, have a lower energy, and then our 2p orbitals. 3s, 3p, 3d. But since our electrons fill starting in the lowest energy orbitals, because lower energy is more stable and the universe always favors low energy, more stability in any system we ever look at. This is referred to as the Aufbau principle. We see that we have 4s orbitals that are lower than the 3d orbitals. Well, what that means then is that the 4s orbitals fill before the 3d orbitals in almost every situation that we will find. The Aufbau principle of filling lower energy orbitals requires this. And if you take a look at a periodic table, you will see that the 3d orbitals do not start showing up for our transition metal elements until we get to row 4, n equals 4. And in fact, the alkali metals and then alkali earths will fill up their 4s orbitals first before the 3d orbitals of the transition metals start to add electrons. And then finally, we also need to consider something called Hund's rules, which says that we will always put in unpaired electrons first for orbitals with the same energy. So if we take a look at our 3 2p orbitals, we see that on the energy scale, they all have the same energy. As we start to populate electrons into those 2p orbitals, we will always put unpaired electrons, one in each of those 3p orbitals, before we start to pair up electrons in the orbitals. You will notice that the farther away from the nucleus, the smaller the energy difference between the orbitals. This again is something that's predicted easily by quantum mechanics. Well, why does the 4s orbital have lower energy than the 3d? It has to do with shielding and electron penetration. So we should have already looked at something called the total radial probability for our s orbitals from an earlier lecture. And what we find is that the 2s and 3s orbitals have nodes of probability that actually penetrate inside of the 1s orbital. That means they are not as shielded by the 1s electrons as the p orbitals are. That means that they are more strongly attracted to the nucleus and lower energy. Our s orbitals have lower overall energy than the corresponding p, d, and f orbitals with the same principal quantum numbers. That means they're more stable than the corresponding p, d, f orbitals when they have electrons in them, and less reactive than the corresponding p, d, and f orbitals. Well, let's use the knowledge that we've just generated to take a look at some electron configurations for individual elements. The first thing that we're going to do is we're going to assume that the orbital energy behavior that we described on the previous slides, which have been calculated for hydrogen, look the same for the rest of the elements. It turns out that the Schrodinger equation, which gives us the quantum mechanical solution for the energy of these orbitals, can only really be solved for the hydrogen atom, where we have only one electron and one proton. As soon as we have more than one electron, it turns out those are too many interactions for us to be able to solve the Schrodinger equation for. So we're making an approximation by assuming the orbitals we've solved for the hydrogen atom also take effect for the other atoms. We're going to talk about ground state. Ground state is where each electron occupies the lowest possible energy orbital that's available. We're going to locate our electrons in the individual orbitals based on energy as those electrons are added as we go across the periodic table. So our electron configurations are going to look the following. 1s will be our lowest energy orbital, followed by 2s, 2p, 3s, 3p. And then you see that we have inserted the 4s orbital before the 3d orbital because it has a lower energy based on the interpenetrations that we had talked about, and then 4p orbitals. In this type of configuration, we are going to stick superscripts directly above these orbitals to indicate the number of electrons in each orbital. So the 1s orbital is capable of accommodating 2 electrons. The 2s orbital is capable of accommodating 2 electrons. The 2p orbital can take 6 electrons. The 3s orbital is capable of taking 2 electrons. But here I've only put 1 electron in that orbital. For an uncharged atom, which atom have I correctly given the electron configuration for? Well, if it's uncharged, that means the number of electrons I have shown here is the same as the number of protons. 2 plus 2 is 4, plus 6 is 10, plus 1 is 11. The element which has an atomic number 11 should be sodium. Go check that for me, please. And we note that group 1 elements have 1 valence electron. They have 1 electron in the outermost shell. We can see that here we have 1 electron in the 3s orbital. In addition to electron configurations, we will also show something called orbital diagrams. And in orbital diagrams, what we do is we show a box that shows each individual orbital that has the same designation. For the 2p orbitals, we have 3 orbitals of equivalent energy, so we show 3 boxes. And now we'll show electrons by arrows, where we have an arrow pointed up for 1 electron, and if we're forced to pair another electron, the arrow will be pointed down, indicating they have opposite spins. So our first electron goes in the 1s orbital. We will give that an up arrow configuration, and we can only pair that with another electron with an opposite spin. We will show a down arrow. For the 2s orbital, again, we have 1 electron with an up spin, 1 electron with a down spin. For the p orbitals, we will place electrons first unpaired in the individual orbitals that have the same energy, orbitals that are degenerative. And then once we have a single electron in those orbitals, if we're forced to add another electron, then we will start to pair electrons up with opposite spins. Well, what's the element that I have just shown the orbital diagram for, assuming that the element is uncharged? Well, I've got 2, 4, 6, 7, 8 electrons. That means I would have 8 protons for the uncharged elemental atom. The element with an atomic number 8 would be oxygen. We have just shown the orbital diagram for oxygen.